This lecture is going to cover solving for moles and masses of reactants and products within balanced chemical equations. If you're unsure still how to balance chemical equations, please go back to that video that's located, I think, 2 or 3 above this one. And also there are extra worksheets and helpful information to help you practice that. It's critically important that you understand how to balance, otherwise you won't get these problems correct. So again, these are abbreviated to go through the math, and we'll talk a little bit about each thing as we go through it. So here's just an example problem, something like you might see on a test. Thermite is a mixture of metal powder with a metal oxide. In the thermite reaction, one metal, usually aluminum, is oxidized while the metal in the oxide is reduced. One example is given below. We say one example because this can happen with several different metals, but the most common one is aluminum because it is easily oxidized. So here they're telling you if you have 1 gram of iron 3 oxide, here's your iron 3 oxide, you have to be able to pick out the compound from the name, okay? If you're still unsure how to do that, go back to the nomenclature naming rules. And they're telling us it's reacted with excess aluminum. The word excess here is critically important because that's one thing that tells us this is not a limiting reactant problem, meaning one of the reactants or the other limits us. In this case, we only have 1 gram of iron 3 oxide and we have all the aluminum our little hearts could possibly desire. So this is not a limiting reactant problem. As soon as you see excess, you should immediately be saying, just do it regular. Just solve this regularly. So it's reacted with excess aluminum powder. How many grams of solid iron are to be expected? Okay. So if I start with 1 gram of iron 3 oxide, how much solid iron will I get as a product? So what do we know? We know that we have this balanced chemical reaction. We know we should always follow the given times the unit factor or factors, and that will equal our unknown. And our given is our starting amount. We have excess aluminum. We know this mole to mole ratio. We know that directly from the coefficients of the balanced chemical equation. So when we look at the balanced chemical equation, there's nothing written in front of Fe2O3, the iron 3 oxide. So it's an understood 1. And there's a 2 in front of the iron, so it's 2. So we have 1 mole of iron 3 oxide is equal to 2 moles of iron. We know the molar mass of iron 3 oxide. We simply add up 2 irons and 3 oxygens. And then we know the mass, the molar mass of iron. So how are we going to get started with this? We have said so far we're always going to do our given times our unit factors equals our unknown. If you do not have a periodic table or the stoichiometry roadmap out and handy, go ahead and pause this video, pull them so you can follow them, okay? Now, our given information is our starting information. In this case, it was 1.00 grams of iron 3 oxide. Now, if you look at your stoichiometry roadmap, we're trying to go, this is what we call a mass-to-mass problem. And we're using a balanced chemical reaction in order to get from the mass of one thing to the mass of another thing by way of going through moles. Always ask yourself, how do I get to moles? This is going to become critically important. So if I have 1.00 grams of iron 3 oxide, the only relationship I have between it and solid iron is the balanced chemical equation here. This is the only relationship I have between them. So the question is, how do I get grams of iron 3 oxide into moles? Well, the answer with that is grams to moles using molar mass. And we've already calculated the molar mass of iron 3 oxide it is 159.69 grams per mole. So grams is going to go on bottom, moles is going to go on top. Okay, now I want to get 2 moles of iron. I do that, excuse me, by way of our mole-to-mole ratio from the balanced chemical equation. And the mole-to-mole ratio, right there. So I want to get rid of moles, Fe2O3, and I want moles of iron, and it was 2 moles of iron to every 1 mole of the iron 3 oxide. Then finally, I'm going to get to grams of the iron because that's what it asked for. So I again am going to use the molar mass, this time of just iron, which I've looked on the periodic table and I can see that it's 55.847. Ah, put it in the wrong spot. Now, you'll notice not only did I write the units of grams and moles, etc., but I also indicated moles and grams of what? Of the Fe2O3 or just the Fe. This way, I don't get confused and put numbers in the wrong spot. So in the green step here, grams clearly cancel, grams of the Fe2O3. That left me with moles Fe2O3. Then I wanted to get rid of moles so I could do it opposite, and I made sure to use the correct number in the correct top or bottom. And then finally I wanted to get rid of moles iron because it's not asking me for moles iron, it's asking me for grams. So if you do the math really quickly, what I'm going to do is I'm going to multiply the top all the way across. So 1.00 times 2 times 55.847. And that's going to be 111.694 divided by the whole bottom multiplied together, which is 159.9 times 1 times 1, which is just 159.9. And my final answer will be, when I divide these, it is 0.6985 grams of iron. Okay? All right. Now, here's another example. Dinitrogen monoxide, N2O, is commonly used as an anesthetic in dentistry. Excuse me. It is manufactured by heating ammonium nitrate. The balanced equation is this right here. Here is our balanced chemical equation. Here is our ammonium nitrate, and we have our dinitrogen monoxide right here, and the water. So it's asking us to calculate the mass of ammonium nitrate. So it's asking for the mass of ammonium nitrate needed to produce 10 grams of nitrous oxide. That's another name for dinitrogen monoxide. It's a common name. So our given in this case is not the reactant. We know we want 10 grams of the dinitrogen monoxide. So the question is, how much ammonium nitrate do we have to start with to break down in order to produce that 10 grams? So it will still be the same process of given times unit factors equals our unknown. But now it's just going to be a little bit in the reverse. Okay. Then part B is to determine the corresponding mass of water produced in the reaction. So this is a little bit two-part. So what we know is that the molar masses are here for you. So we have the molar mass of the NH4NO3, the molar mass of the N2O, and the molar mass for water. And we also know, based on the balanced chemical reaction, that there's 1 mole of ammonium nitrate for every 1 mole of dinitrogen monoxide, and there are 2 moles of water for every 1 mole of dinitrogen monoxide. Now, we get these numbers directly from the balanced chemical reaction. See, when there's nothing written out front, it's an understood 1. Okay, those are terrible 1s, but those are supposed to be 1s. And then the 2 there. All right, so for the first part, again, is your given times your unit factor or factors equals our unknown. Okay, now the only relationship we have between the dinitrogen monoxide is moles. The only relationship we have between the dinitrogen monoxide and the ammonium nitrate is moles. How do I get to moles? I get to moles, my grams to moles, using what? Molar mass. So the first step here is to convert to moles of dinitrogen monoxide. Once I have moles of dinitrogen monoxide, I can convert those moles to the moles of the NH4NO3 needed to make that 10 grams. And we're going to do that with our mole to mole ratio directly from the balanced chemical reaction. So this is step 2 here. We're taking the moles of dinitrogen monoxide and we're using our coefficients from our balanced chemical equation to convert moles of dinitrogen monoxide into ammonium nitrate. So now we know we have 0.227 moles of ammonium nitrate needed in order to get 10 grams of dinitrogen monoxide. Our third step is to take those moles of ammonium nitrate and then converting it to grams of ammonium nitrate. And we're going to do that with the molar mass. So this is step 3. So our moles of ammonium nitrate multiplied by the molar mass here of ammonium nitrate gives us 18.2 grams of ammonium nitrate. So what this means is we need to start off, if we want 10 grams of dinitrogen monoxide, we need to start with 18.2 grams of ammonium nitrate. When we start off with that 18.2 grams, it's a reasonable amount because we only got 10 grams of the dinitrogen monoxide, and also water was a secondary product. So it makes sense that the amount we would start off with would be more than we actually get. Part B of this said, okay, now that you know how many grams of the ammonium nitrate you had to start with, and you know that from that amount you got 10 grams of the dinitrogen monoxide, how many grams of water did you get? Remember conservation of mass. And no, we cannot just subtract. You cannot just say 18.2 minus 10. That doesn't work. Okay, doesn't work. So what we have to do is we have to take the moles of dinitrogen monoxide, which is what they've done here, and convert it to moles of water. Why? Because the only relationship we have is between the dinitrogen monoxide and the water are the coefficients from the balanced chemical reaction. So we know when we go and look at this, we can say for every 1 mole of this, we get 2 moles of this. For every 1 mole of this, we also have 2 moles of this. It's a 1 to 2 ratio. The balanced chemical equation allows us to convert between two different things within the chemical reaction. How do I get to moles? In this case, you've already solved for moles. You did it back here in part A. So we know how many moles of dinitrogen monoxide we have. And so we're going to use the relationship between the coefficients of the balanced chemical equation to convert between moles dinitrogen monoxide and moles of water. So when we do that math, we get 0.454 moles of water. And then we just use the molar mass to go ahead and convert the moles back to grams using, again, molar mass. So the summary is when we have a mass-to-mass problem, they're giving us mass and they're giving us the mass of one thing and they're asking us for the mass of something else. That's a mass-to-mass problem. We're going to go from grams of the given to moles of the given to moles of the asked for to grams of the asked for, or the unknown. Okay? And we're going to do this by way of molar mass and the mole to mole ratio, which are the coefficients from the balanced chemical reaction.